Hello, future engineers. Welcome to my YouTube channel. This video presents solutions to counter diagonals, then 3 problems on construction of influence lines, and 1 problem on the analysis of a space truss. So if you're still new to my YouTube channel, don't forget to subscribe, and so that you will be updated to all future videos that I will be uploading in YouTube. And I hope that these lecture videos will help you in your studies. So it will also inspire me to do more lecture videos. So please enjoy watching. So the first example, for the beam shown below by the basic method, construct the influence line for reaction at A, reaction at B, moment at D, shear just to the right of A, shear just to the right of B, moment at B. Also compute the maximum values of RB, moment at D, moment at B, and the shear at D due to the combined effects of the live concentrated load of 10 kilonewtons, uniform live load of 3 kilonewtons per meter, and uniform dead load of 0.8 kilonewton per meter. So for reaction at A, so we apply reaction at A. Of course, AX is 0, and the unit load, position it anywhere on portion AB. Distance from left is X, so 12.5 minus X from B. So summation moment about B equals 0, clockwise positive. So we have RA times 12.5 minus 1 times quantity 12.5 minus X equals 0. So RA is equal to 2 over 25 times quantity 12.5 minus X for X greater equal to 0. So we can now plot when X is 0, RA is 2 times 12.5 over 25, so that is 1. When X is 4.5, 12.5 minus 4.5 is equal to 8. Then 8 times 2 is 16. 16 over 25 is 0.64. Then when X is 12.5, this is 0, so RA 0. Then when X is 16.5, then we have 12.5 minus 16.5 times 2, negative 8 over 25, or negative 0.32. Then for RB, summation moment about A equals 0, so we have counterclockwise positive, RB times 12.5 minus 1 times X equals 0. So R sub B is 2 over 25 of X for X greater equal to 0. So plotting, when X is 0, RB is 0. When X is 4.5, RB is 9 over 25 or 0.36. When X is 12.5, 2 times 12.5 or 25, RB is 1, of course. Then when X is 16.5, RB is 33 over 25 or 1.32. So then we compute for RB maximum. So RB maximum is equal to 10 times 1.32. So we have to place the live concentrated load over C because the ordinate is maximum, and because the entire influence line for reaction at B gives us positive area for the entire span, then we have to load also the live load over this entire span. Since the dead load is also over this entire span, then it is equal to 3 plus 0.8 times the area under the influence line. So 0.5 of 16.5 times 1.32. That's the area under the influence line. So RB max is equal to 54.582 kilonewtons. Next, for MD, so we draw the free body diagram from A to D. So the position of the load is here for the portion 0 to 4.5. So the distance from left is X. Then from point D, it's 4.5 minus X. So we apply the positive shear and the positive moment at D. So positive shear downward if it is in the right section. Positive moment is counterclockwise if it is in the right section. So summation moment about D equals 0. So MD plus 1 times quantity 4.5 minus X minus RA times 4.5 equals 0. So MD is equal to 4.5 RA minus 1 times quantity 4.5 minus X. So when X is greater than equal to 4.5, this unit load here is no longer in this free body diagram. It's on the other segment of the beam. So we remove its contribution to moment, which is this. So what is left is 4.5 RA. So for x greater equal to 4.5, moment at D is 4.5 RA. So when x is 0, then RA is 1, 4.5 times 1 is 4.5 minus 1 times quantity 4.5 minus 0 is 0. Then when x is 4.5, this is 0, so 4.5 of RA is 0.64, is 2.88. Then when x is 12.5, RA is 0, so 4.5 of 0 is 0. And when x is 16.5, RA is negative 0.32, 4.5 times negative 0.32 is negative 1.44. So based on the figure, then we can compute the maximum moment. The concentrated live load should be over point D. The ordinate is maximum. And we only load this portion with live load. Take note, the dead load is covering the entire span. So for the live load, uniform load, we have to compute this area. But for the dead load, we have to compute this combined positive and negative area. So therefore, maximum moment at D is 10 times 2.88 plus for the live load, 3 times quantity 0.5 times 12.5 times 2.88. Then for the dead load, 0.8 times quantity 0.5 plus 12.5 times 2.88 plus 0.5 of 4 times negative 1.44. So the maximum moment at D due to the combined effects of these above mentioned loads is 94.896 kilonewtons. Then for shear just to the right of A, so which is here. So if we draw the free body diagram of the support and just to the right of A, then this is the situation. So summation versus y equals 0, RA minus V sub A just to the right equals 0. Then that means that shear just to the right is equal to RA. Now remember that when x is 0, the unit load is here and RA is 1. So RA, which is 1 minus 1 is 0. So shear just to the right of A is 0. Then beyond that, it is equal to RA. So we have to copy the influence line for RA. So I just also indicate this, that this is the influence line for shear just to the right of A. Now let's proceed to the shear just to the right of B. Shear just to the right of B. So we may draw FBD from A to B or B to C. So it's up to you. So let's select B to C just to the right. So this is the free body diagram just to the right. RB is not involved because we are considering a section just to the right. So the positive shear is upward because this is the left section. That's the right section. For the right section, it is downward for positive shear. Then we also have positive moment, which is clockwise, supposedly. Then this is the free body diagram. If the unit load moves from A to support B, so the unit load is no longer here. So that means summation versus y equals 0. Shear just to the right of B is 0 from A to B. So shear just to the right of B is 0 for x 0 less than equal to x less than equal to 12.5. Then when x is more than or greater than 12.5, the unit load enters. And therefore, the equation would be shear at B just to the right minus 1 equals 0. So that's the equation. Shear at B just to the right minus 1 equals 0. So shear at B just to the right equals 1 for x greater than equal to 12.5. So we are now ready to plot. So from A to B, 0. Then it jumps to 1 constant from 12 for x greater than 12.5. So that's the influence line for shear just to the right of B. And finally, we have moment at B. This is B. Then if we look at the moment diagram of B, which is this, when just to the right or just to the left, the moment at B is 0 when the load moves from A to B, because the unit load is still on the other side. So summation moment about B equals 0. So MB plus nothing equals 0, or MB plus shear then times 0 because we sum up moment about B equals 0 is 0. So MB is 0 from 0 to B, and when the unit load enters from for x greater than equal to 12.5, then we have MB, summation moment about B equals 0, MB just to the right plus 1 times x minus 12.5 equals 0. So MB just to the right equals 0 for 0 less than equal to x less than equal to 12.5, and MB just to the right plus 1 times quantity x minus 12.5 equals 0. So MB is equal to negative of quantity x minus 12.5. This is for x greater than equal to 12.5. So we can now plot the moment diagram for influence line for MB. 0 to 12, then it becomes when x is 12.5, 0. When x is 16.5, 16.5 minus 12.5 is positive 4 times negative 1, so negative 4. So that's the influence line for moment at B. Then for the maximum moment at B, maximum moment RB, maximum moment at B, then we have RA. So let's have the shear diagram for shear at D first, influence line for shear at D. So this is the free body diagram from 0 to 4.5. So summation versus y equals 0, RA minus 1 minus shear at D equals 0. So shear at D is RA minus 1 for 0 less than equal to x less than 4.5. 4.5 is not included for shear. Then for x greater than 4.5, if you look back this free body diagram here, the unit load is now on the other side. Then the forces left are RA and shear at D. So you remove minus 1 here, then the remaining equation is the shear equation for x greater than 4.5. So shear D is RA for the case x is greater than 4.5. So let's now plot. So for 0 to 4.5, RA minus 1. So when x is 0, RA is 1, minus 1, so 0. Then when x is just to the left of D, RA is 0.64, so 0.64 minus 1 because it is still just to the left. So 1 is still in the span. So 0.64 minus 1 is negative 0.36. Then for x greater than 4.5, it is equal to RA. So let's copy 0.64 down to negative 0.32. So that's it. Because shear at D is equal to RA. So negative 0.32. So the maximum shear is, if you compare the negative areas with the positive area, this positive area is greater. The fact that its length is equal to 8 meters and the height is 0.64 compared to 8.5 combined, but the height would be lesser than the magnitude of 0.64, which is 0.64. So the concentrated live load should be placed just to the right of this point D here to maximize the shear at D, and the maximum shear at D is positive for this case because of this big positive area. Then the live load would be placed over this positive portion, while the dead load, of course, we cannot adjust that. Then it covers the entire span, and for the dead load, we have to compute all these areas. So moment maximum at D is 10 times for maximum moment at D at B rather is, this is the diagram. So it is equal to 10 times negative 4. So you have to place the concentrated over this point. Then the area plus the live load should be placed only here. even if there is dead load but there's no area here, so it has no contribution. So the live load is over this negative portion, and it is equal to 3 times quantity 1/2 or 0.5 of 4 times negative 0.4. So 3 live load, and remember there is dead load also included here. So 0.8, then quantity 0.5 times 4 times negative 4. So MD max is equal to negative 70.40 kilonewton meter. Then next is MD max, it's already true. Then shear D max here is equal to 10 times 0.64 plus 3 times 0.5 of 8 times 0.64, then plus the dead load 0.8 times this area 0.5 of 4.5 times negative 0.36 plus 0.5 of 8 times 0.64 plus this area 0.5 of 4 times negative 0.32. So computing maximum shear at D is equal to 14.968 kilonewton meter. So that's it, the solution for this problem here. Okay, let's have problem 2 about influence lines. For the beam shown, construct analytically the influence lines for reaction at A, moment at A, shear at C, and moment at C. So we have a cantilever beam. For reaction at A, so we have to apply the reaction and the unit load, of course, you can place it anywhere at a distance x from A as our origin. So the equation is simple as RA minus 1 equals 0. And this is applicable for all x in that interval of the cantilever beam. So RA is equal to 1 for x greater equal to 0, or for 0 less than equal to x up to 7.5, the entire span of the cantilever beam. So it means it is constant, it is 1 from A to B. So that's the influence line for RA. Next, for moment at A, so same diagram, we just apply the positive moment at A, which is clockwise. Then summation moment at A equals 0. Our equation is MA plus 1 times x equals 0. So MA is negative 1x. And again, this is from for 0 less than equal to x less than equal to 7.5. So that means when x is 0, it is 0. When x is 2.5, it is negative 2.5. And when x is 7.5, negative 7.5. So negative 2.5 here and negative 7.5 there. Influence line for moment at A. Next is the shear influence line for shear at C. So from 0 to 2.5, this is the free body diagram. And we have shear going down as positive direction. And that's the moment at A, positive moment at C. But the equation is summation versus y. So it is RA minus 1 minus shear at C equals 0. So shear at C is equal to RA minus 1. And because RA is constant, it is equal to 1 from A to B. Then 1 minus 1 is always 0. 1 minus 1 from A to C rather. So 1 minus 1 is 0. So for 0 less than equal to x less than 2.5, then shear at C is equal to RA. Because it is no longer part of the free body diagram, it now moves on the other span CB. So RA equals shear at C. So from 0 to 2.5, RA is 1. So 1 minus 1 is 0. So this is for x greater than 4.5. RA is equal, shear at C is equal to RA. And RA equals 1. So it is 1 beginning just to the right of C. But 0 to A to C, it is 0 because RA is always 1 from A to C. Then from C to B, just to the right of C, it is equal to RA, and RA is equal to 1. So that's why it is 1 up to B. So that's the influence line for shear at C. Then for the moment at C, so we draw the moment diagram for the portion C to B. So we have shear at C, it's now upward. Then we have moment at C clockwise at the left. Then this is the free body diagram when the unit load is still on the span A to C. So if we sum up moment about C, so M sub C plus nothing equals 0. So that means MC is 0 when the unit load is still moving from A to C. So that's why MC is 0 for 0 less than equal to X less than equal to 2.5. But beyond that, the unit load is now on this span for 0 less than equal to X less than equal to 2.5. So then we have summation moment about C equals 0. So MC times this distance is X minus 2.5. So MC plus 1 times X minus 2.5 equals 0. So M sub C is negative of 1 times quantity X minus 2.5. So when X is 2.5, this is 0. When X is 7.5, 7.5 minus 2.5 times negative 1 is negative 5. So for X greater equal to 2.5, that's the formula. So for M sub C is equal to 0 from A to C, then it becomes 0, then it is negative 5 at the end B when X is 7.5. So we apply this formula here. That's the influence line for M sub C. Then that's it. And that's the complete construction of the influence lines. So let's have problem 3 for the beam shown. Construct analytically the influence lines for reaction at A, shear at B, reaction at C, reaction at D, and the shear just to the left of C. So first for RA, we have to construct free body diagram up to AB. So RA, REX0, then we have the unit load distance from A is X, and we have shear at B, or reaction at B. So summation moment at B equals 0, so we have RA times 9 minus 1 times 9 minus X equals 0. So R sub A is 1 over 9 times 9 minus X, and this is applicable for 0 to 9. Then when X is more than 9, so the unit load is now moving from B to D. The unit load is no longer here. Then if you sum up moment about B, then we have RA times nothing equals 0. So that means RA is 0 for X greater than equal to 9 meters. So we can easily construct it. When X is 0, RA is 1, and X is 0. Then when X is 9, it is 0 here. Then 0 everywhere beyond B, as defined by this equation. Yeah, that's the influence line for RA. Then we have for shear at B, summation moment at A equals 0. So shear B times 9 minus 1 times X equals 0. So it is 1 over 9 of X. So when X is 0, it is 0. When X is 9, it is 1. And for X greater than 9, the unit load is no longer in this free body diagram. So shear at B times 9 plus nothing equals 0. So that means shear at B is 0 beyond 9. So for X greater than 9, shear at B is 0. So it is 0 at when X is 0, 1 when X is 9, but just to the right of 9 onwards, shear at B is 0. So the FBD looks like that. So this is the influence line, influence line for shear at B, or reaction at B, vertical reaction at B. Then next, reaction at C. So let's draw the free body diagram of the portion from B, C, and D. Then when the unit load was still in the portion AB, then action, reaction. So we have shear B going down. So that's RC, assume upward, RD, assume upward. Shear at B assumed, or shear at B is not assumed. These are assumed upward because we always assume positive reactions. And this one is natural because from action-reaction principle. So remember that there is value for shear at B from 0 to 9. Beyond that, shear at B is 0 from B to D. So to derive R sub C, we sum up moment about D. So R sub C times 9 minus shear at B times 17 equals 0. So R sub C is 17 over 9 of V sub B. This is applicable for 0 less than equal to x less than equal to 9 meters. Then when x is greater than 9, then V sub B is 0. However, the unit load enters. So that is 0, but there is now unit load. Distance from the left is x, from point A is x. Its distance from D is 26 minus x. So this is x minus 9, and its distance from D is 26 minus x. So summation moment about C equals 0. So we have RC times 9, then minus 1 times quantity 26 minus x equals 0. Take note that V sub B is no longer involved because it is 0 when the unit load enters from B to D as manifested in this influence line here. So R sub C is 1 over 9 of quantity 26 minus x for x greater than equal to 9 meters. So we now plot when x is 0, R sub C is 17 over 9 of 0, so it is 0. When x is 9, this is the formula. 17 over 9 of 1 is 17 over 9. So it is 17 over 9 there. Then just to the right, using this formula, 26 minus 9 is 17 divided by 9. So it's also 17 over 9. When x is 17, this is the applicable formula now. 26 minus 17 is 9, divided by 9 is 1. And when x is 26, 26 minus 26 is 0. So it's 1 here and 0 at the other ends. Influence line for R sub C. Next, influence line for RD. So we sum up moment about C equals 0. Take note that the unit load is no longer here because we consider first from 0 to 9. So RD times 9 plus V sub B times 8 equals 0. So RD is negative 8 over 9 of V sub B. This is for 0 less than equal to x less than equal to 9. Then when x is greater than 9, so the unit load is here, and remember V sub B is now 0. So summation moment about C equals 0. By the way, the distance of unit load from C is 17 minus x. So that is 17 minus x because this is 17 then minus x. So R sub D times 9 plus 1 times quantity 17 minus x equals 0. So RD is negative 1 over 9 of 17 minus x. And this is for 9 or x greater equal to 9. Or 9 less than equal to x and x less than equal to 26 meters. That's the other way. So let's plot. Negative 8 over 9 when x is 0, V sub B is 0, so it is 0. When x is 9, V sub B is 1. So the influence ordinates, the ordinate to the influence line for RD is negative 8 over 9 here. And when x is 17, this is now the formula. And 17 minus 17 is 0, so it's 0 there. Then finally when x is 26, 17 minus 26 is negative 9 times negative 1 over 9, so 1. So 0 here, then 1 at the end. So this is the influence line for reaction at D. And finally, for shear just to the left of C, so you may draw FBD for portion BC or for CD, including the reaction at C. So this is the free body diagram for the movement of the unit load from A then just to the left of C. This is the free body diagram. Then when the unit load is now on the span CD, then we just put it there. So considering this diagram, positive shear at C just to the left is upward because it is now the left section. So this is the moment at C just to the left. So R sub C plus RD plus V sub C just to the left equals 0. Summation versus Y equals 0. So V sub C just to the left is negative of quantity RC plus RD. And this is for 0 less than equal to X less than 17 range. Then what if it is now greater than 17? So the unit load enters and summation versus Y equals 0. The equation would now be RC plus RD plus shear just to the left minus 1 equals 0. So shear just to the left is equal to 1 minus quantity R sub C plus RD, or 1 minus R sub C minus R sub D, because I'm talking about minus quantity RC plus RD. So this is the formula for X greater equal to 17. So when X is 0, then we have negative of R sub C, 0, RD 0, so it's also 0. When X is 9, when X is 9, this is still the applicable formula. So we have negative of R sub C, negative of 17 over 9 minus or negative of quantity 17 over 9 plus negative 8 over 9, so it is negative 1. So 17 over 9 minus 8 over 9 is 1. Then negative of 1, so negative 1 here. Then when X is just to the left of C, or 17, just to the left of 17, so this is still the applicable formula. The value of R sub C is positive 1, and the value of RD is 0, then it is equal to 0. It is equal to, this is the applicable formula. R sub C is 1 and RD is 0, so negative of 1 plus 0, so negative 1. So it means it's constant. Then when X is just to the right of 17, this is now the applicable formula. So 1 minus R sub C, which is 1, so 0 minus 0, so it's 0. Then for X greater than 17, so when X is 26, 1 minus R sub C, which is 0, minus RD, which is 1, so it is everywhere 0 beyond 17 meters. So this is the influence line for shear just to the left of C. So for problem 4, knowing that the maximum tensile strength of the counter diagonals that are made of ropes is 1,500 newtons, determine the safe value of P. So we have here the truss, and we have here the counter diagonals which are made of ropes. So let's solve for RB so that we can find the shear in its panel, and let's determine or identify the panel which is critical here. So the panel which is critical here is the one with the greatest shear. So summation moment about G equals 0. So let's have the By, and we have the horizontal reaction 1.8p, but we sum up moment about G, so it's not involved. This one is not involved. So By times, we have 6 at 1.2 meters, so this is 5 times 1.2, so 6. By times 6, then minus 2p times 7.2, minus p times 4.8, minus p times 3.6, minus 1.5p times 2.4, minus p times 1.2, plus 1.8p times 2 equals 0. So solving for By in terms of P, By is equal to 4p. So if By is 4p, then the shear here should be 2p downward, because we already have 2p here. So 2p downward, then 2p minus p is p downward, then p minus p, we have zero shear in this panel here, DE. So the most critical panel is panel BC because it has the greatest panel shear. Then because the shear is going down, it means that force in BK is in compression, and therefore because this is made of rope cannot resist compression, it is zero. So this is tension, member CL or LC, and BK is compression, and when it is in compression, it is zero. So we equate the tensile strength of each rope, which is 1,500 newtons here, to the panel shear. The vertical component of 1,500 equated to 2p, so that we can solve for p. Now we compute this angle theta. Arctan of theta is opposite to 1.2 divided by adjacent 2. So 1.2 over 2, so theta is equal to 30.964 degrees. The vertical component of this member in tension, LCL, is FCL cosine theta equals 2p, or must be greater than equal to 2p. Then this is equal to 1,500. Cosine of 30.964 must be greater equal to 2p. Therefore, p must be less than equal to 643.1 newtons. So that's the safe value of p. Then we have a space truss. So the truss shown consists of 9 members and is supported by a ball and socket at B, a short link at C, and 2 short links at D. Determine the force in each member for P equals negative 1,900 Newton J, or the load is going down 1,200 newtons, and Q is 0. Can you find a zero force member? Which member is it? So based on the figure, so let's identify the zero force member first based on the principle of finding zero force members. So we have an unloaded joint here, joint E, and we have 3 members that are on the same horizontal plane. There is only a member EE which is not on the plane. Therefore, if you sum up forces vertical, perpendicular to the planes, these 3 forces will not be involved, only this member will be involved. But since there's no force to be counteracted by this member, so FAE, cosine of the angle it makes with the y-axis, equals 0. So that means FAE is 0. So the zero force member is FAE. And we now assume the component reactions at each support. So we have ball and socket at B, 3 reactions. At C, only 1. At D, 2. dy and dx, dy and dz, and at C we have cy only. Then distance AB is square root of AB. Along x is 0.75 AB. Distance AB, sorry, along x, this is the x-axis, is 0.6 square, plus along y 3 square, then along z 0.75 square. So distance AB is 3.15 meters. Distance AC is square root of 1.2 square plus 3 square plus 0.75 square. So that's 3.317. Distance AD is square root of along x 1.2 square, along y 3 square, along z 2.25 square. So we have distance AD 3.937 meters. So you use your calculator to verify these distances. Then distance AE is not important because it is a zero force member. Distance CE is square root of along x 1.8 square, along y 0, along z 3 square. So square root of 1.8 square plus 3 square is 3.499. That's distance CE. So the zero force member is FAE. And let's assume all members in tension as shown in the figure. Then let's compute the reactions first. summation moment about BCX. So FAE, take note, is 0. Summation moment about BCX considering the entire system by right thumb rule. So if you use your right thumb, then dy is positive because it is upward and it curls positively. So dy times 3 minus 1,200 times 0.75 equals 0. The other reaction components are not involved because they pass through BC. dz passes through BCX. So dy is equal to 300 newtons upward. Next, summation moment about BZ equals 0. So by right thumb rule, we have Cy times 1.8 positive plus 300 times 1.8 minus 1,200 times 0.6 equals 0. Of course, DZ is not involved again because it is parallel to BZ. So minus 1,200 times 0.6 equals 0. So Cy is equal to 100 newtons upward. Then summation moment about CDZ equals 0. So all these are not involved. By right thumb rule, 1,200 is positive. So use your right thumb. 1,200 times 1.2 minus BY times 1.8 equals 0. 1,200 1.2 minus BY times 1.8 equals 0. So BY is equal to 800 newtons. Then summation moment about dy equals 0 by right thumb rule. So negative dz times 1.8, then no more, equals 0. So dz is 0. So summation forces along z, so bz is also 0. So beginning with b, at b, summation forces y equals 0. So we have FAB times 3, vertical component of distance 3 divided by 3.15, then plus by, which is equal to 800, equals 0. So FAB is negative, so it is compression. 840 newtons compression, FAB. Then summation forces along x equals 0 at b. So we have, take note, bx is 0. So we have FBC plus the z plus the x component of FAB. So FBC plus negative 840 times 0.6 divided by square root divided by distance 3.15 equals 0. So FBC is 160 newtons tension. Then summation forces along z at b equals 0. Take note that BZ is also 0. So positive in this direction, opposite to the z-axis. So we have FBE plus negative 840 times 0.75 over 3.15. So component of FAB equals 0. So FBE is tension, 200 newtons tension. Then we proceed to joint C. Summation forces y equals 0. So we have FAC times 3 divided by distance 3.317 plus CY, which is equal to 100, equals 0. So 100 plus FAC times 3 over 3.317 equals 0. So FAC is negative, so it is compression, 110.57 newtons compression. Then summation forces along x equals 0. Then we have positive in the negative direction of x. So we have FCE times 1.8 divided by distance 3.499 plus the x component of negative 110.57 times 1.2 over distance 3.317 for FAC, then equals 0. Plus 160, which is FBC. There is FBC, 160 equals 0. So solving for FCE, it is equal to 233.3 newtons. It is negative, so it's compression. Then summation forces along Z equals 0. So positive in the negative Z direction. So we have FCD plus FCE, which is negative 233.3 times 3 over 3.499. then plus the z component of FEC, which is negative 110.57 times 0.75 over distance 3.317 equals 0. So FCD is positive, so FCD is 225 newtons tension. Then we proceed to joint D, summation forces along Y equals 0. Then we have dy 300 plus FAD times 3 over distance 3.937 equals 0. FAD times 3 over 3.937 plus dy 300 equals 0. So FAD is negative, so it is compression. 393.7 newtons compression. Then summation forces along X equals 0. Then positive in the negative direction of X. So we have FDE plus negative 393.7 times 1.2 over distance AD, which is 3.937 equals 0. So FDE is positive 120 newtons tension. So everything is found. Then all you have to do is check joint A. So you have to check joint A. Summation forces X, of course, positive in the X direction. So we start with FAC, which is negative 110.57 times 1.2 over its distance 3.317 plus FAD, which is negative 393.7 times 1.2 over distance 3.937, then minus FAB. FAB is negative, so minus of negative 840 times 0.6 divided by distance of AB 3.15. So let's check if it is 0. This is positive, the two are negative, so almost 0. So okay, summation forces Y equals 0. So negative going down as positive, negative 110.57 times 3 over 3.317. Then negative 393.7 times 3 over 3.937. Then AB, AB is compression, so negative plus negative 840 of 3 over 3.15, then plus 1,200 going down positive, then combined, then it is almost 0 also. So okay. Finally, summation forces along Z is equal to negative 110.53 times 0.75 over 3.317, the Z component of FAC. Then AB, negative 840 times 0.75 over 3.15 distance, or AB. Then minus FAD. FAD is negative 393.7 times 2.25 over 3.937. So computing that, it is also equal to 0. So that checks and verifies our answers.